Hello everyone, this is lecture 10 of Advanced Drilling, PTRE 451545. Today we should be finishing module 1 and starting module 2. There is no more equations. I think in module 1, it's just some stuff, basic stuff that I want to overview. And then we'll be moving into module 2. Before I start though, any questions on the homework that is due tomorrow midnight?
Okay, when I saw you, I wanted to, sometimes when we are multiplying, there could be, for example, if you multiply 0.052 times 9.62 times 10,000, for example now.
That's 5,000?
No, if we multiply it, we can get like 4,999.
Okay, small error.
So those, I don't know if someone now get like maybe difference of 12 feet and someone use 5,000. So is it still the same, or we should always approximate to?
Yeah, it's a round of error, I guess. They call it round of error. There is two types of errors. One is round of error, which is what you are describing. The other error is it's called truncation error. We do that in simulations. Every iteration you have a small error, and then it gets bigger, bigger, and then you are off by a lot. Yeah, I guess within some logic, in the oil field in general, they cannot really mix you a math that is on the second decimal that easily. So that 9.62 really would become either 9.6 or 9.7 in the oil field. I never heard of I remember we were having, when we were registering in the mud weights that they were measuring in the mud tank, they were measuring the mud weight coming in and the mud weight coming out. They were putting it in as like this. Look at that, 12.1 plus, it meant 12.1 heavy, or 12.1 minus, like light. It's like this. I mean, there is some, if you tell your mud engineer, if the mud engineer tells the mud hands, go mix me a 12.13 mud weight, it's not going to happen. They're going to calculate for 12.1 or 12.2 to be on the safe side. Yeah, small error. I mean, as long as it's logical. Also, you understand when the changes are big versus small, right? When you do your homework, like if the difference that if you are using generally what I will do is that I will use as many decimal points as I can or carry on the answer so that I use all the decimal points, and then at the very end round up or down accordingly to a logical decimal place.
Like if someone that gets 15,024 will be rounded up to 15,000 feet.
Yeah, is that for a static fluid level?
Yeah, for a static fluid.
Which basically means on the surface.
On the surface.
Regardless of, yeah, that means, so it's the same answer. You are 24 feet above the surface. It's considered, yeah, you are going to say, give that 15,024 value and then say at the surface. Yes. So, because then if you say at the surface, it's like you heard it from somebody and you wrote the answer down. So how you got there? But you calculated a value that is bigger than the TVT, right? So that's why, that's the logic behind the answer that you gave, which it sounds like you know why you are writing at the surface and not anything else. Anyway, so any other questions? We still have tomorrow, so if you really have any problems, you can swing by or send me an email. It should be an easy homework. I will try for the next homework. Ideally, I want to do it Monday, the 24th.
Okay.
Yeah. But I'm gonna see if I can make it the 26th, the Wednesday.
Well, I think if you come early, better we playing around there. But that also depends on how we have covered so already.
Yeah, I want to cover the material that I want to cover. And then because I want to do the homeworks, and then module 2 is gonna be important, and it's gonna be on the exam. There is an exam coming up on March, March 20th, and it's after spring break. I'm trying to manage all this stuff. So if I cannot do it on the 26th, it's gonna be on the 24th. The thing is that last year it was on the 22nd, the second homework due. So I don't want to push things too much because of there is also a project coming up on the iPhones and stuff like that. And I kind of want to give as much time after the exam for the blowout stuff the well-controlled stuff that we're gonna be doing. Okay, last time we finished talking about BOPs. We basically introduced the blowout prevention system or the well-controlled system, which the main component is the blowout preventers, and we talk how they work and how they operate basically, and what they are used for. And if you want to see one, you should go to Dracula, and there is one downstairs that is semi missing parts, etc. But you can see how it looks like. And we said that it's one of the strongest, probably the strongest equipment in the rig. Like if the rig catches fire, this is gonna stand there. It's expected to stay there and take as much damage as they can. Also, when people are when people are they have bad intentions, like in the Gulf War, they were exploding those to cause fire. And then when you explode those, you are basically igniting a source that keeps coming from the earth. So it's like you get fuel coming up and you are burning it all the time. So it's very hard to deal with it. But this was man-made, I guess, trouble. It was during a war. Yeah, anyway. So we are gonna talk about offshore drilling. I don't know why this is not I made some changes on the slides, but nothing really crazy. What was it that I made? I think we had a typo in one example problem. I fixed it.
I was
This one.
referring to 4. Yeah, 6.
Yeah, and I made the statement shorter, and then so it wouldn't be an issue. Something else I changed, I don't remember. I don't think it was something serious. It was just the wording. I made it simpler anyway. So today we are gonna finish module 1 by talking about offshore drilling. It's something that I didn't really do in the first class, the undergrad class. I did go over it, I think, very briefly. In order to go over it a little bit in more depth in this class. So the first offshore well was drilled off from a pier in California, 1897. It was the Summerland field. So you have a pier, just like in a port, you have a pier and you walk and you have the boats on the side. This is how it was. You walk on the pier and you are on the rig. Beautiful place, actually, if you ever visit. And that gave birth to the offshore drilling business, which I wouldn't say it was rapidly developed. It was late-ish in last century that it really got going on and on and on. And the first out-of-sight, specially designed steel platform was installed in the Gulf of Mexico. I guess we have to change that name too.
Gulf of America.
Yeah, in 47. And that was by Kerr-McGee. Kerr-McGee, let me tell you, an adapt component in 2006. Kerr-McGee. And that was a rig that you couldn't see from the land. Okay, it was far inside, but it's very dirty waters actually. They are 14 feet water depth, not terribly deep, but you couldn't see. It was like a proper offshore rig, like we have today, in a sense. Although today we are in crazy depths. Now this rig, you can visit it if you are ever in Louisiana in, what is it? I knew a girl from that town. What's the name? Not the lake. The rig's name is Mr. Charlie. The name of the place it is Morgan City. Yeah, Morgan City. It's a little bit out of Baton Rouge. And it's the first transportable, submersible offshore drilling rig and an industry springboard to the current offshore rig technology. It's a museum now, basically. You pay and visit it. It drilled hundreds of offshore wells from 1954 to 1986. It's now a museum, rusty museum, I guess. And those places that it used to drill, it was very, very shallow waters, but dirty waters, like the marshes. Louisiana is known for basically muddy marshes and the swamps and this kind of stuff. Like if you go into that water, you don't know what is under you. Very dangerous. And this is how it looked like in its prime. It was a it was a technology jewel at the time. It was, it was built and it was used like Mr. Charlie is the name. This is how it looked like. Modern day offshore operations, we use what we call mobile offshore drilling units, MODUs. And there are two types. Bottom supported units, those are touching the floor, the sea floor. And that's the ones that I said in Louisiana, you have a lot of shallow waters that is in the marsh. So the seabed is not very steady, but you can have it touching there. Or floating units, which are like a boat, sort of, in the sea floating. Modules are mostly used for exploratory and appraisal wells. Fixed drilling platforms, see later, are used for the development wells. Remember, we said 3 well types. Exploratory is a wildcat well. You are brand new in the area. It's the first well that you drill there. Then you have the appraisal wells, which is, there is oil there. You are trying to find the limits of the reservoir, look at how the reservoir properties vary throughout the reservoir, the field. And the development wells is like you made your plan for those wells and you are drilling them as part of, we're going to inject water here, produce oil there, blah, blah, blah. They are very well designed wells for your project. And for that, you are not going to use modus. You're going to use fixed drilling platforms. By the way, the information for those slides is from that book, Fundamentals of Petroleum, 2011. It's not from your red book, the Applied Drilling Engineering. Now, bottom supported units, several categories: submersibles, jack-ups, floating units. You have inland barges. That's the ones they use in Louisiana. Drill ships and ship-shaped barges, semi-submersibles. And this is how it looks like, this picture schematic from Maersk. You have an onshore rig on the right, and then you have a barge. Barge has a flat bottom. Okay, that's a barge. It's the shallow, that's the Louisiana stuff. Jack-up is very practical, and it can only go to 550 feet, but you can basically adjust for the depth with those legs, that you can adjust the height of the rig, and also you are stable because you are touching the ground. So it's some advantages here. Now, semi-submersible, yeah, it's moving. but it's in deeper waters, of course. And the drill ship is basically as deep as you can go. Now we are on the 8th generation of drill ships. I believe the one in the picture is 6th generation. But yeah, we're much more advanced. Actually, remember when I was telling you about dual gradient drilling? Back in 2014, Chevron had, I don't know if they still have it, they have a drill ship specially designed for dual gradient drilling, to allow dual gradient drilling. And we're going to see in the last module why this is important for offshore operations. It helps you with the casing design. Now, semi-submersibles can be posted barges. A barge hull is the boat part, that the bottom, with several steel posts supporting a deck. Bottle type submersibles have several steel cylinders, we call them bottles, holding the deck. And in general, it's pretty stable if it touches the seafloor. Arctic submersibles, they are specially designed for drilling in moving ice when seawater freezes. These are specially made for the Arctic or for icy environments. And I forget the name of this company. It's a Dutch company, I think, that starts with H. And they have rigs that are shaped very uniquely designed rigs. Homan, I don't remember the name of the company. So this is in Louisiana, barge, inland barge. I think you understand that it's a flat bottom, and you have basically you have to push it with tugboats to get it to the place that you want. It's fairly conventional technology, so it's not the most developed technology available. This is a jack-up rig. Jack-up rig, you have to be able to recognize it from the legs. 550. This is in the North Sea, and you see behind a drill ship. But this one is a small one. It's a baby one. You can drill up to 550 feet depth, highly stable, easily movable, and yeah, inland barge, another inland barge.
How?
Yeah.
How do the jack-up one? How does it the legs being anchored on the seabed? Is it that they cement it?
No.
Or how do they jack it? Because down the seabed probably will be muddy, and then probably the weight might be making a ship trying to.
Well, it's like an anchor that goes into the sea floor. Now, if you want to move the inland barge, you can bring a drill ship that goes under it and then lower it to touch the boat and then lift the legs up, and then you can move it. So you move it most of the time with the help of a ship that has. So you want a ship to come here, get under it, then lower this red part to touch the ship, and then lift the legs and move. Okay, it doesn't move on its own. It doesn't have a mechanism. The drill ship moves on its own. And yeah, but this is, and inside they have, it's not really a luxury hotel, but they have a lot of stuff. They have catering, they have grill option, fried option, they have table tennis, they have offices, they have the living quarters. But yeah, I mean, you're always constrained by space, always. This is an inland barge. Again, must be Louisiana. Those waters are crazy. Flat bottom and flat sided, towed to the drill side, obviously. it does not have a mechanism to move. You need to push it with another boat or drag it with another boat. Sometimes the hull is flooded and the unit becomes semi-submersible. Swan barges are generally used in shallow waters. This is actually a swan barge. You know what is a swan, right? It's like, yeah. Yeah. I remember when I was driving from Austin to Baton Rouge, Louisiana, in the morning, I was waking up at 3 a.m., trying to leave at 3:40, and then I would drive off and try to beat the Houston traffic before 9 to be on the east side, the other side of Houston, and then drive to Louisiana, off to Louisiana, and then the goal was to be in the office before lunch, like 11, and then
And you go back to Texas the same day?
No, I was driving from Austin to Louisiana, but I was passing by a lot of swamps in the morning hours, and you will see like on top of them, like a fog on top of them, because they are ecosystems of their own. Yeah, they have alligators inside, they have snakes, they have a lot of stuff.
Crocodile.
The crocodiles are for sweet water, yeah. Oh, sorry, crocodiles are for salt water, yeah. But if you really want to see alligators, if you go to Florida, Everglades in Florida, okay, 1 hour from Miami. If you drive down the west side of Florida, which is the Gulf side, and you go to the bottom, you hit the Everglades, and then you cut across 1 hour, and you are in Miami, and then you're on the east side, you're on the Atlantic side of Florida, but that's where it's called Alligator Alley. It's Everglades. I think it's the national park. It's considered a national park. They don't do any drilling there, but I bet you there is oil underneath there if they look, because of the way that those marshes are deposited, it creates overpressure regions. But yeah, you don't want to be in this water. So 1 hour from there, you have marshes, alligators and stuff. I went there on October of 2022. And then 1 hour from there is like very, very aristocratic schools where they do sailing and stuff. So it's like you go from one side to another side very quickly, I slept in my car outside of the Everglades Museum one night there because I was driving, and then the next day I was in Miami. But it was, I think it was early October. You couldn't really see the fog there as much as, but I remember when I was driving to Louisiana and you see the swamps, you really see the fog on top of it. Like it's very, very visible from far away, actually. Anyway, drill ships, they are streamlined bows and they have square sterns. Deepest water drilling capacity is 10,000. They can do 12,000, 15,000 these days on the 8th generation. Stationed by anchors, several anchors, or thrusters and propellers. And generally speaking, you are going to use this method these days. It's dynamic positioning.
Yeah.
You have them propellers facing each other, and you apply thrust or variable thrust on each to keep it stationary. And stationary means it will still be moving, but moving within a allowable range. Also, you know that the marine riser is flexible, but it has its limits as well, right? So you don't want it to move too much. Now, in case you have a very, very bad storm, you can disconnect the marine riser and let it flow hopefully it won't get cut or anything, and you flow on top of it, the boat, and when the storm ends, you connect again. In case that these things are gonna happen. Very, very deep waters. Very, very deep waters. This is how the thrusters look like. You see they are facing each other. So you basically apply thrust this way and that way, and you're trying to balance it. It's very, very high tech. Like if you watch the movie Deepwater Horizon, that girl in the movie was doing DP dynamic positioning. Semi-submersibles looks like this. You have the columns and you have the pontoons at the bottom, which is like a, you know, the boat type, the catamaran boat that has two lines, you know? No.
Canoe.
No. It has two of those. It's very
They
similar.
use it for sporting. This one they use for sporting.
No. They have a sail. I'm talking about this kind of boat. You see, it has two.
Okay.
That's how they use the same principle. Where is it? It uses the same principle with this, but the thing is that for the semi-sub, why it's considered is called semi-submersible. This is submerged. It's under the water, but it's the same technology or the same principle that they are using. In fact, it's Archimedes principle. You have the deck, and then basically the deck is a rig floor. And bracing, holding it together. It's sturdy and can operate in rough waters. Column stabilized, consists of two or more pontoon-shaped hulls attached to several vertical columns. Sometimes they are self-propellable, but they are not going to be going very fast. Other times they are carried on ships, like I said earlier, bigger ships in this case than with a jack-up rig. Now, concept and design. You see the anchors, you see the pontoons. Well, ballast is basically used as an anti-weight, weight holding, balancing something. So you have the deck, etc., etc. You know, on a rig, I don't think I have a picture. You know the opening on the rig where you see the seawater at the bottom in the middle of the rig. You know what is this called by any chance? Moon pool. I should have had a picture of that. Oil rig, moon pool. Moon pool. This one where you see the water in the middle of the rig.
Yeah.
This one is the moon pool. The opening is called the moon pool.
They have to open that. What?
Because you need to have the well going through to go into the water, right? Yeah. Anyway, now fixed drilling platforms are used for development wells, so they are more rigid, compliant platforms, larger than modus, and can carry large equipment required for production operations. Also, I would say that many of those fixed drilling platforms, the goal is they will drill the wells and then they will eventually become production platforms. So you are basically having them temporarily to do the drilling, and then you are going to use them as production platforms. So those are designed a little bit differently. They are more comfortable. They have more facilities. They have more space. They are bigger. They require, the transportation is harder. The design is more complex, etc., etc. Some examples of rigid platforms: steel jagged platform, concrete gravity platform, saison type platform. These are, it gets heavier, even it gets like compliant platforms are GUI tower platform, tension leg platform, spar platform. These are, as the name says, rigid, like they are hard on the ground, you know. These are more like moving. Steel jagged platform built on its side and at some point launched into the water, floating on its side while the jacket continues being constructed. I will show you pictures. Lowered to a vertical position as the legs come to rest on the sea floor, the mat line. Sometimes the jacket is lowered over pre-positioned pilings, and the remaining components are placed using cranes. By the way, there is a lot of types. I would say, somebody said once, I don't remember who, that there is no two platforms or rigs that are the same with each other, right? They all have. So when we say categories, it's a little bit of a loose term. Let's see the picture of this. You see, it's huge. They build it like this, and then they are going to lower it down. So the lowering operation is very, very heavy. It's like you need to plan it step by step. It's almost like launching a rocket to space. You need to make sure everything is going to work. And a lot of things can go wrong, and probably they will. So you need to be able to overcome this. Now, concrete gravity platform, you see a lot of those in North Sea, actually. And North Sea is more, it's tougher waters than the Gulf because it's open, you know. A lot of cement for this, a lot of cement. And basically the weight is gonna hold it in place, so you want it to hold. Heavy enough for gravity to hold it in place, constructed in protected waters near shore, and then floated to vertical position. Tall saisons, columns, this stuff, made of steel, reinforced, are the dominant features. That's one type, but this is a small one actually. Design, some of them are designed specifically for use in Alaska's Cook Inlet. And this is because you want the legs to be able to handle friction with snow and ice, okay? Because it makes them very, very scoury, it's called. It makes it very, very, it's interpreting them very easily, okay? Oops. Tidal currents carrying pack ice destroy the steel jagged platforms. The drilling production deck rests on top of 4 saisons made of 2 layers of thick steel to prevent damage by ice scouring. So those saisons, yes, they are concrete, but you will have around them steel, okay, to be able to handle the friction with the ice, which is worse than friction with water or anything. It's like a very bad upgrading that you can have with ice. GUI towers are less expensive to build than the rigid platforms, such as steel jagged, concrete gravity, and steel saison platforms. Jagged is held to the seafloor via GUI towers to clamp weights. They are less stable, obviously, than the rigid platforms, but they can handle deeper waters. they can be placed in deep waters. And obviously, if you are going to have them in place for a long time, you need to take special care of them, okay? It's not like, oh, it's a permanent structure, it's going to stay there. I mean, those tension leg, I mean, the tendons, you need to replace them every now and then, etc., etc. And you need to make sure that where it's touching the floor is okay. Tensional platforms are fixed to the seafloor with steel tendons. It's like they are anchored to the floor. And then spar platform is a weird shaped platform moored to the seafloor via counterweight. And Anadarko had one. And when they were installing it, it was a big thing. And when they came over to Texas to give us a lunch and learn, they were showing us picture of that. I think it was Anadarko. I don't know Anadarko or Apache. I think Anadarko. Yeah, they are moored to the seafloor with counterweight, so you transport them laying down and then you drop it. Some are connected to the seafloor like tension platforms, because here you see the tendons. So it's like a tension platform, but it's not really a tension platform. Yeah.
Where is the Mori? The Mori? Yeah.
Is at the moored to the seafloor, dragged down to the seafloor, or sank down to the seafloor.
Okay, I remember those operators in Ghana, they were saying that they have issues with that Mori, and I was wondering how is the equipment.
Well, you're gonna transport it like flat, like laying down, and then you are gonna let's see. Let me show you. Let's go to Google, Mr. Google, and say mooring spar platform. We see the same picture, but you basically drop the weights down, and it's supposed to rotate, but it's a very, very hard process. It's a very hard process. This is a nice picture. Maybe I should have used it in the slides, but anyway, I will do it another time. Maybe next year, if we're still around. May have submerged pontoons or columns like those of semi-submersibles. Yeah, it's what I said, that they are, you never have one type. Everyone is different from each other. So when we say categories, spar, basically it's about this shape. That is like a spar. A very, very expensive operation, of course. Oh, there you go. That's being transported. And then we are gonna drop it. Okay, that was the end of module 1. Any questions on the offshore stuff? Okay.
So someone, Dr. Lee said in the past, drilling offshore is not possible because the wave can cause the pipe to break.
Yeah.
So what did they use to? I can't remember.
Well, it's like what I said with the drill ship. The marine riser is allowed to move, but it has its limits. You can, if you bend it too much, things are gonna start breaking. Well, in Louisiana, because it's shallow waters and fairly steady, you could drill. You could put something that touches the bottom. I mean, if you're dealing in 10 feet water, 10 feet is this room, basically, right? Okay, you can put something that touches the floor, the seabed, and stay stationary. And in that case, it becomes like a onshore well, basically. And not much will affect you. But if you want to go deeper, and then you are After 550, when you make the transition from jugger to semi-sub, that's when you start getting motion, because the jugger touches the floor, right? It has those things, the towers touching the seafloor, and it's not supposed to move at all. So at that stage, yes, you can use you can consider using a dry blowout preventer on the deck or something. But after that, semi-submersible, you have the blowout preventer on the seafloor, and then the marine riser up to the rig, and the rig is moving, and then you need to control this motion. And then you are from the semi-sub, you are in deeper stuff like the drill ship, etc., etc. But I want you to be able to make the distinction of modus and platforms. So this is an important, no, where is it? Yeah, this is an important slide, because what we have seen before this slide is modus, right? And then we went to the offshore drilling platforms, which is for more permanent usage, basically. Because this stuff, this stuff is for fancy wells like Wildcat and this kind of stuff, like Macondo, for instance, Deepwater Horizon. It was semi-sub, I believe. But when this is how you will drill your Wildcat, this is how you're going to drill your appraisal wells. But once you move into the development portion, then you are going to use the platform, because you want more space, you want more capability, and then these are most likely going to become production platforms after that. You're going to make some changes on them, and they're going to become production platforms. So that was the end of module 1. It took 100 slides, over a month to go through. What did we learn? Main items involved in drilling operations, drilling rig functions and main components equipment, introduction to casing design using mud window. The most important thing is that you learn the YouTube model and how to use it.
The almighty YouTube model.
Safety equipment, wellheads and BOPs, offshore drilling rigs and platforms. These are the stuff that we learned. But all the equations that we have seen in module 1 had one common thing. What was that common thing?
Only one?
All the equations that we have seen, all the math that we saw in this module had something in common. What was that in common?
You're talking about it. The 0.0. Is it 0.0?
Yeah, but I mean, what was the same for all of them? I'm not talking about the number.
This is the formula. So
Yeah.
it's static.
Exactly. Yeah. Very nice. Static condition. So things were not moving. Right? You don't consider things moving. Now in module 2, we are gonna start having things moving. By the way, this lecture, I'm gonna put it into not this folder. I'm gonna put it in the next folder here. Okay, so the recording. I will send an announcement. Anyway, so when things are moving, you have friction, and you need to take that into account. And this module will always be a lot about friction, dynamic stuff. Dynamic comes from the Greek word dynamic, which means power. And in scientific language, it has to do with time-dependent stuff. And generally speaking, when we say dynamic forces, we mean time-dependent. And in our case, it's friction. Think of friction. Okay. This is an overview of the rig hydraulics. And it's something not really new for you because you have seen the circulation system before.
Yeah.
Okay, you have seen it. So you know, we start from the mud tank, we get sucked into the pump gives you pressure, expels through the discharge line, high pressure. Then you go up the standpipe, you make a measurement of the pressure, standpipe pressure, then through the hose, into the swivel, down the Kelly, down the drill string, through the nozzles of the jet, or the jet nozzles of the bit, up the annulus, on the way out, and atmospheric pressure through the flow line. Now, in every step, and these are all the steps that we have, surface equipment, inside the drill pipe, inside the drill collars, through the bit nozzles, especially through the bit nozzles. Drill collar annulus, drill pipe annulus. The fluid is moving, right? So it brushes against the walls of the conduit that is moving, and it basically loses pressure to friction. Okay, just like we said, okay, the fluid is moving, in the surface it's moving up and down, but it's not moving by much up and down, right? It's basically, let's just say the surface the same height, the same depth. But then when you go downhole and you start going down, you go deeper and deeper and deeper, and you have more and more weight above you, right? So we add pressure because you have more weight above you. And this is what you learn with that 0.052 number. You add more weight above it. It's the hydrostatic weight. And then you lose height, and you come back to the surface. So whatever height you are going to gain, depth you are going to gain, and increase the pressure, you're going to lose it when you come back up, right? So you are going to say the well is 10,000 feet deep. I'm going to gain 10,000 feet of mud above me. That's the hydrostatic weight. That's the 0.052. And then I'm going to lose it when I'm coming up. But throughout the whole process, I'm going to lose pressure throughout the system because of friction, from the beginning to the end, right? So there is friction losses associated with all these components in the surface equipment, in the drill pipe, in the drill collars, through the bit nozzles, through the annulus of the drill collar and the borehole, through the annulus between the drill pipe and the borehole. So I'm losing friction as well. So the pressure I need to inject the fluid with downhole, say from the pump downhole, it needs to account for all the friction that I'm going to lose as well. Because we said we are going to gain pressure because of the weight of the fluid above us, and then lose it because we're going to come back up. But at the same time, we are going to lose pressure due to friction, and we are not going to gain this pressure that we are going to lose through friction. So we need to take that into account in all our estimations. Basically, when we pump downhole, we need to give mud that pressure that it's going to lose to friction. Anyway, and of course, the YouTube equalities are still valid. Okay, what you learn in the YouTube model is still valid. It still can be used. So how does it work? Drill pipe pressure at the standpipe, more or less. Surface pressure losses associated with it are still outside the YouTube model. Still outside the leg, I guess. Then on the leg is what you, as you go down the left leg, you gain pressure because you have more and more fluid above you, but you also lose pressure because of friction. Okay, and then you go through the bit nozzles, or the collars first, BHA. Okay, you lose more pressure to friction, but gain more pressure because of more weight above you. And then you cut across the bit. The bit, let's just say, doesn't have any height. So negligible gains from more depth. I mean, how tall is a bit? Like a foot and a half? Okay, you don't gain a lot of pressure because of hydrostatic hydrostatic, but you lose a lot of pressure because of friction across the jelly nozzles. And this pressure is very important. And then the other way, I go through the annulus between the drill collars and the borehole. It's a tight squeeze there. I lose pressure because I'm going shallower and shallower and shallower, but I also lose pressure because of friction at the same time.
So how do you cater for that those pressure that you're losing due to friction as you are?
How can I afford?
Yeah, how can you cater for that?
How can I care? Do you mean how
Like-
can I measure it?
Yeah, how can you make sure that you reduce the losses or to counter it so that it will not have a
Well, reducing the loss to friction is by making the conduit bigger. That means if I can drill my hole bigger and make use a smaller pipe inside or bigger pipe inside, sorry, it's gonna be less friction. But I can't do much about it. Now, if you mean how am I gonna measure it, it's very hard to measure it directly. And they use correlations that are like as old as I am to use them. And people come up with better correlations. It hasn't been investigated a lot, I would say. But you can never be, you cannot do it mathematically accurately because these are like, it's empirical stuff that they use, like based on experience. You have models that measure it for you, but it's not done directly, analytically, with a map. Because if you think about it, I mean, you guys took well completions, all the equations that we saw, did you see any equation that had time in it? Not really, right? It's very, very hard to dynamic estimations. Because also, bear in mind, this friction changes based on how fast you are pumping. So if you are pumping at 100 strokes per minute, you are dealing with this kind of friction here, this kind of friction, this much friction there, this much friction there, this much friction there. Then you increase your circulation. How are you going to adjust? I mean, it's new values now that you are dealing with. You can adjust, approximate stuff, but it's not good enough. It is not, it can be sufficiently okay, but it's not accurate. Anyway, then you come back up, and on the surface pressure, on the surface should be atmospheric pressure. Now, as atmospheric pressure, how do you get from here to here?
You use an incline.
Yeah, use gravity. Exactly. Very, very nice. Very nice. Use the gravity to get there. But again, the YouTube model is valid. It's always valid. So you learn about this 0.052 equation, and this was a static mud weight, right? Things were not moving. How do I incorporate that value? Those dynamic frictional losses. I need to use a dynamic mud weight value. And that is, yeah, all calculations presented in module 1 involve static mud weight, non-circulating conditions. During mud circulations, the effective weight exerted by the mud is higher than the corresponding static mud weight due to pressure losses to friction in the circulation system. So, say I'm drilling a well with a 9.62 ppg mud weight, but I'm circulating. That means when I'm pumping it down, I need to pump it at a pressure that will account of the pressure losses in the system to make it come up. Otherwise, it won't come up. If I'm pumping mud down cold and it's coming up, even at zero pressure, it's coming up, it still comes up at zero pressure. That means I'm giving it enough pressure when I'm pumping it to be able to make it back to the surface. So I'm giving it all the pressure that it's going to lose to friction. Because remember, I'm pumping it from the surface and I'm going to get it back at the surface. So whatever depth I'm going to gain, I'm gonna lose eventually. So that's zero, right? But I'm still pumping it at a certain value, at a certain pressure. So that pressure, say 800 psi, if I'm pumping at 800 psi and I'm getting it out at 0 psi, atmospheric pressure, it means that throughout the system, I'm losing 800 psi to friction. And these are not recovering. They are lost. They are heating up the drill string. They are heating up. It's like when you hit the brakes of your car. When you accelerate, you brake, you make chemical energy to mechanical motion. And you accelerate, 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 and then you hit the brakes. The brakes convert this motion into heat of the brake pads. And that you never recover. You need to hit against the gas, make more motion, but you will never recover. That's why many times on the highway, you may be consuming less fuel than in the city if you stop and go, stop and go, stop and go, you know? Well, at relatively same conditions, let's say. Okay, these dynamic mat weights we are going to talk about are equivalent mat weight, telemarketers. Equivalent mat weight, EMW, is very important, and equivalent circulating density. If you took an undergrad class in drilling, you probably learned the equivalent circulating density, this ECD term, but you didn't learn the equivalent mat weight. ECD is an equivalent mat weight value at specific conditions. So they are the same thing. EMW, ECD is an EMW value at a certain location, at a certain depth, blah, blah, blah. So ECD is an EMW value, but EMW is not ECD. EMW can be a lot of stuff other than ECD. And we're going to see when we learn how to do the hydraulic loop, which is very important. Pressure losses are developed using empirical correlations and computational models. It's very hard to do it analytically. It's impossible to do it analytically. Analytically, I mean equation-wise, mathematical equation that you solve explicitly. You either need to do experiments in the lab, like use a hydraulic loop, and like the one we have, and bring it at certain conditions and measure stuff, or you need to use a computational model that basically solves a lot of equations at the same time, and even then, you still don't have enough information. You need to add some sort of empiricism in them. Okay. We have time to do the hydraulic loop. I want you to pay special attention on the hydraulic loop because you are not going to find information about it online. There is one book that has information about it. H. Rabia, 1978. Oil well drilling, something like that, the title. That has information on it, but YouTube model, you might be able to find it. Most people use the YouTube model for well-controlled scenarios. I like to use it for everything that I can possibly use it. And you can, once you understand it, I think you can find helpful information. Hydraulic loop, it's a little bit harder to learn. So I want to pay attention when I do it, so that you will be following. You will be able to follow. It's not hard. It's not hard. It's important. Okay. So the hydraulic loop is a diagram that shows how does the mat weight varies throughout this circulation system. Okay, throughout the bit, going down and then coming back up. It has as you see here, pressure on the horizontal axis and depth on the what is it, the vertical axis, true vertical depth, okay? And it goes from the beginning of the well to the bottom of the well. Now, we started here, okay? We started here. But we said we are measuring the pressure on the standpipe, right? This is SPP. And let's just say SPP is somewhere here. SPP is basically the drill pipe pressure, okay? The left side, left leg of the YouTube model, okay? What happens from SPP up to here? I want you to ignore these changes in depth. They are negligible, okay? So forget if the fluid gains depth or loses depth. I would say it's the same depth, okay? Very small stuff. But you have something, other changes there. What are they related to?
There's going to be change in since pressure and then the friction.
Friction, okay.
Yeah.
Is it gonna, so how will that affect the pressure? If I measure the pressure here, and assume I have a measurement here, how is the measurement here gonna be in relation to this? Is it gonna be bigger or smaller?
Less than.
Less than, yeah.
Smaller.
So I'm expecting to move a little bit to the left. But I'm about the same depth. I ignore how much depth I gain. Then I'm here. I'm moving into the same conduit, okay? And I'm going deeper. That means I have more weight above me, but I'm also losing pressure to friction. Overall, I gain pressure. The value becomes bigger because I gain more, I have more fluid above me than the fluid that I have, than the pressure that I'm losing moving down there. So let's just draw it like this. What is the slope, by the way?
Sorry?
The slope.
0.05. That would be the.
What are the units of the slope?
PSI per foot.
Yeah.
Are you sure?
It's like
Yes.
Why are you sure? Is
like
the slope PSI per foot?
Yes.
Yeah.
That's changing pressure by change the depth.
Sorry, let me move this here to see. Are you sure it's PSI per foot?
Oh,
Okay.
the slope. That's
It's
feet
yeah.
per PSI.
The other way. Okay. So now that I'm moving to the collars, how do you expect the slope to change? I'm going to tell you something. The inside diameter of the drill collars is smaller than the inside diameter of the drill pipe. So it's something like this, very narrow.
Yeah.
So you expect to have more friction. So how do you expect the slope here, which I haven't drawn yet, to change? When I'm going from the drill pipe to the drill collars? Do you expect it to become bigger or smaller? And he said that the slope is feet per PSI. So if you are thinking things in terms of PSI per foot, inverse. So do you expect it to be a steeper line now, or like this, less slope? How do you want me to draw it? Like this, or like this?
If the pressure gradient becomes bigger because it's smaller, if you inverse it, it should be smaller.
Okay.
So I hope I'm not making a mistake.
No, to me, I think one, the nozzle is small. There is a lot
No,
of.
you are not at the nozzle yet.
I want to say the collar, the drill collar, that place is smaller than the drill pipe.
Yeah.
So there is going to be a loss of
Pressure
friction
drop.
loss and pressure drop. So, but in terms of the hydraulic, the more the
I think it should be smaller.
It should come this way. It should come to be a little bit going big, small, tilting this way.
You are gonna see the second homework with numbers, but it's gonna look something like this.
It should be smaller.
Let me. Something like this. Let me do it better. You see the change? Like
Less
this.
steeper.
It became steeper.
Okay.
Okay. Now I'm at the nozzles of the bead. Now I go at the nozzles. The nozzles of the bead are very, very tiny. And I have a lot of frictional losses.
It becomes more steeper.
Huh?
It becomes more steeper.
More steeper, or but we said something.
No.
No height.
Okay, no, all right.
No height. So I ignore the height of the bead. Okay, in the picture it has a height, but in real life it has a height. But do I lose pressure or gain pressure? Because you don't know it yet, but the way you see it, okay, on the surface I lost pressure. Then downhole, I gain pressure net. I gain and lost, but net was gain. And then in the drill collars, I gain, lost, net was gain. And now I'm at the bead, I'm only gonna lose. I'm only gonna lose if I ignore the height of the bead, right? I'm only gonna lose, and I will lose a lot. So it's gonna look like this.
Yeah, because it comes out from the.
Yeah, it just loses to friction.
Yeah.
And this is basically the PB. Just the PB by you.
So why are we ignoring the eyes?
If height of the bead is, if I go the bead here, it could be this height. If you did it with height, it will look something like this. It wouldn't be a problem, but it will look something like this. Or, sorry, something like this. If you did it with height. Tiny, tiny height. On the grand scheme of things, this diagram is not, the schematic is not to scale. It shows the bead to be very tall, the drill collars to be very short in real life, and the drill pipe very, very short. Because the well is much longer than this, it goes like very long. So what I'm drawing is not really the accurate representation. I mean, you're gonna see in the second homework how, but generally we draw it like this. Sorry. Like this. Now, and this is PB. Now, going back up, I'm now here. I'm at the annulus between the drill collars and the drill pipe. So I'm going up, and I'm losing pressure because I have less fluid above me as I move, and I also lose pressure to friction. So it's gonna look up something like this. Right? And then I'm gonna go in this annulus, which is steeper. Sorry, it's wider, and I'm gonna again lose pressure to height, but also lose pressure to friction. But I know that when I'm here, once I make it out of the well and I'm here, pressure will be zero, right? So I'm basically gonna come back up here, CP equals to zero. So I'm gonna go basically like this. Right? And that's the hydraulic loop. By the way, this slope and this slope are not the same. Okay? It depends. Because It depends on the clearance that you have here, the gap, and the inside of the drill collars that you have. I'm just making in general, there would be a change of slope. I don't know if it's gonna be like this or like this, but there would be a change of slope. Every time the width of the conduit that your fluid is moving through changes, you have a change in slope. Okay, it's just, I don't know, it depends on the values that you are given in the homework or exam or whatever. It could be, yeah, and also this change here is tiny. I make it a little bit too much in this example. But generally speaking, you start from DPP, which is approximated by SPP. You lose pressure on the surface, you go down, gain pressure because of depth and lose to friction, then go further down, gain pressure due to depth and lose more pressure due to friction, cut across, losing pressure in the bead nozzles, and then get back up in the annulus between the drill collars and the drill pipe, and then go back to zero on the surface. Okay, this is the hydraulic loop. And what if you are doing reverse circulation? It's still the same, it's just this is gonna be CP and this is gonna be DPP, right? It's gonna be different values, so the slopes will change, etc. But because now you are going down from the annulus, you are losing friction and gaining weight here. And then, so this is going to be a different slope. And then this will be a different slope. And then, yeah, but still, it's the overall shape of the hydraulic loop will look like this, yeah. So this is the hydraulic loop, which you won't find a lot of that in the literature. That's why I wanted you to pay attention. And this is how it will look like. I think the homework will make it clearer because you will be given the values from and you will have to basically draw it yourself. And I think when you draw it yourself, you'll understand how it works. Okay, now I need to show it. Come on. How do I show what I drew? Oh my God. Okay, let me draw it again. DPP, surface, down, 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 CP. Okay, now, okay. At this depth, what is my pressure? My pressure is this value, right? At this depth, my pressure is this value, right? Okay. Can I say at every depth I have a pressure, right? Yeah. In fact, at every depth I have two pressures most of the time. The inside the drill pipe and then yeah, okay. Can I divide?
Can I ask a question?
Yeah.
Will it, in the case of static, it used to be equal?
This is dynamic.
It's not going to.
This is dynamic. Yeah, static was equal because only the depth mattered. Now you have friction. Very good point. Very good point. Now, at every depth, I have a pressure. Okay. Can I take that pressure and convert it to a density? Because I have pressure and I have depth. And you know the equation with a 0.052. Can you take the pressure here and convert it to density? Say the pressure is X. The pressure is X, P1. No, I want to use the same. Pressure P, and TVD value, pressure T at TVD depth. Okay. I take this pressure P and I divide by 0.052 TVD. I get something in units of ppg, right? Something density-wise, a density equivalent. Okay, that I will call EMW, the equivalent mat weight. So if I ask you, what is the equivalent mat weight here? you find the pressure here, and you find the depth there, and you convert that to density, and you're gonna tell me the EMW at this depth inside the drip pipe is this much. And then you might say, okay, on the other side, on the annulus side, at this depth again, the EMW is this much. This is actually, EMW is the actual density that the rock is feeling, or the tubulars in place at that depth are feeling. So you may be using a different density, but the actual density, the equipment in place that it's feeling, it's that EMW. And you're gonna get it from the hydraulic loop. You can find me an EMW anywhere along this loop, right? Okay, you can find me an EMW everywhere along this loop. But if I ask you for this value here after the beat, okay? It's an EMW value, right? I said you can find me the EMW anywhere along the hydraulic loop. But that point here, the EMW is identical to ECD. We call that ECD. ECD is more well known. Huh?
Below the beat.
Below the beat with only the annulus left. Basically, the mud made it to the beat through the nozzles of the beat and only has to go through the annulus. So this particular point here, and I was trying to draw E here. This is E. Okay, that is the ECD. This is the ECD. It's a special value of EMW. But EMW is available all throughout the loop. That's the important thing. So if I ask you to give me EMW at a specific depth, you give me two values. But if I ask you for ECD, you just give me one specific EMW value at that point. And actually, the ECD, generally speaking, is not the case, but unofficially is with the bead supposedly on the touching the bottom as well, but it may not be always touching the bottom. It might be a little bit lifted up. Then the EMW that you are, the ECD that you are calculating is still ECD, but yeah, you know, it's still an EM. You still gonna use the same equation to calculate it. In the homework, it's not touching the bottom. It's a little bit. You have a little bit of a gap. And you can still give me the ECD at that point. Anyway, any questions on the hydraulic loop?
They're not there today.
Yeah. I went to teach the other class on yesterday. Okay. And I went like 1 minute before the class was starting, and there was a professor there, and he told me 5 minutes. 5 minutes.
Wow. He's counted. He was counting you.
He told me to wait 5 minutes.
I thought you were a student.
No, he
has nothing to do with this class.
Oh, he wasn't
Wow,
finished.
wow.
It's not giving him counting the minutes.
Wow.
Yeah, he told me we'll give you 5 minutes. I think he was doing a review ahead of a final.
Okay.
Yeah. Anyway, but if you have any questions on the hydraulic loop, let me know. You have about a weekend to digest it, and then we're gonna carry on next on Tuesday, and I'm probably gonna give you guys the homework, the 7th homework by then. So by tomorrow night is the first homework, and then but hydraulic loop is the most important thing of module 2. So we already covered it. It won't get any harder than this. I don't think it's going to get any harder than this. But I want you to know the hydraulic loop because I cannot really give you any resources outside of the
notes.
Of the notes because I don't know any book that they have it yet. Yeah. So yeah, let me know if you have something, if you didn't understand something. Anyway, thank you very much. I will see you on Tuesday. And good luck with the homework.
Thank you.
Yeah, thank you, Tito.